Hello. In this lecture, I will be talking about two topics that are interrelated with each other: impulse and momentum. I will begin with the concept of momentum. So, momentum, and I'm sure a lot of you have studied it back in your previous physics classes. It has the symbol P, and it is basically equal to the product of the mass times the velocity. Okay, let me explain to you the concept of momentum through some example. Uh, Suppose you have a brick wall, okay, and well, let me draw some bricks there. Bear with me. Something like that. It's not the prettiest wall, but and so on. Okay, so let's say you have a brick wall in front of you, and let's say you and I are standing at some distance away from it. Um, you are holding in your hand let's say a gun, all right, and the gun shoots a bullet. Suppose the bullet is a 22 millimeter, which is basically a small bullet. It's about the size of a cigarette filter, okay? Uh, so the bullet is small in size, so the mass of it, let's call it small letter m, but it's very fast, right? So it goes something like maybe at least Mach 1, maybe one time the speed of light or something like that. I am, on the other hand, I'm holding a big boulder, okay, a big rock. So this is a bullet here, and I'm holding a boulder, and it's massive, okay? I could hardly carry it and lift it above my head. And both of us now, of this almost at the same time, we're going to hit the brick wall with the bullet and with the boulder, all right? Which one do you think will make more damage? The bullet or the boulder? Remember, the boulder is big. I have asked this question in classes for many, many years, and have always gotten roughly 50-50. Half the student would say the bullet, the other half would say the boulder. Or maybe I should say that the number of students who say boulder and bullet are equal, but there is also some, about say 30% of the students who have no opinion on it. I'm one of them, actually, because I've never tried this experiment before. So why the confusion? Why everyone is confused on it? Some people say the bullet, some people say the boulder, and another third would say something like, I'm not sure, I don't know. Why are they confused? The reason that they're confused is because, you can pause the video and think about it before I give you the answer. But the reason that they're confused is because the bullet has a very small mass, but it's extremely fast, all right? So when it hits the wall, it would have a damaging effect because of its speed. The boulder, on the other hand, it's very slow. Let's say I am going to throw it with my own body, with my own arms. So it's not going to go very fast. Remember, the bullet is going something about, something in the range of 340 meters per second, which is about the speed of sound. Maybe double that or triple that, I'm not sure, but let's say it's that. The boulder, on the other hand, it's probably going something like, at best, maybe 5 meters per second or 7 meters per second or something like that. So it's pretty slow. However, the boulder is very massive, okay? So the damaging effect on the wall due to the boulder is because of its mass. And the damaging effect of the wall due to the bullet is because of its speed. Make sense? So here we have a combination of two things, mass and speed. Now imagine a boulder at the speed of a bullet. Okay, here in this case you will have something like an artillery shell. Something extremely damaging. It will basically go through the wall, make a hole, and just continue on the other side of the wall. You see what I'm saying? So when we talk about momentum, P, which is the product of m times v, so you can see what momentum now is. It's basically, it gives you information about the collisional power. These are not the right terms, but I hope you understand what I'm trying to say here. The collisional power, or the damaging effect of, or the collision, between two objects. How strong that collision, or how effective is that collision, is generally measured by what we refer to as the momentum. Okay? That's really the essence of momentum. If you look up your book, it will say the momentum is a quantity of motion. Totally abstract definition but this example, I hope it will illustrate to you what momentum is. Okay? For example, another quick example. Imagine you have a small car, such as a Honda Civic or something like that, going say 60 miles an hour, and then on the let's say on the other lane you have a big semi truck, 18-wheeler. I'm not going to draw 18-wheel, but you got the idea. It's moving at, let's say, also 60 miles an hour. Okay, as you can see here, of course, the momentum of the truck is much greater than the momentum of the small car. Again, if you are, if you cannot digest the word momentum, just think of the collisional power, or the quantity of motion, I guess. So, however, if I say that, let's say this semi-truck, suppose it's going, say, 10 miles an hour, okay, really slow, but let's say that the Honda Civic, or this small car, suppose it's going, say, 100 miles an hour, okay? So there is a probability here that probably both would have the same momentum. I'm not sure. We need to calculate that. So how do you calculate it? Well, you go P equals mv. So you want to calculate the mass of the car, the small car here, times 100 miles an hour converted into meter per second. And then the same thing for the semi-truck, you see what I'm saying? And then you would compare which one has a greater momentum. You get that? So that's basically what momentum is. I'm going to talk more about momentum later on, but I want to come back to the concept of impulse, and then I'm going to combine the two later. Okay? So what is impulse? And the reason I introduced momentum first is because I cannot really tell you about impulse without you knowing about momentum. Okay, so when you think of the word impulse, think of a force, okay? It is a force that is imparted or exerted on an object within a very short time, okay? We do impulse all the time, we just maybe don't think about it. For example, when you kick a soccer ball, okay, that's impulse. The time of contact between you and the soccer ball is extremely short, something like in the order of tenths of a second. And let's say I'm playing soccer with you and I pass the ball to you. So now the ball is coming towards you. And let's say it's going at some speed, say 5 meters per second or something, slow, it's coming towards you. Now you kick the ball with your foot, with your shoes. And what happens, the ball is in contact with your shoes for a fraction of a second. And then after that, after you hear the sound, you see the ball going in the opposite direction at a much larger speed. Let's say it's coming with 5 meters per second. Now it's going at, say, I'm guessing, say 15 meters per second or something like that. So the force that you have imparted or exerted on the ball, we call, times the time of contact, we call that the impulse. Okay? That's the essence of it. Again, let me give you an example. I'll show you a picture of that. Oh, another example of it. Let's say you're playing golf. So with your golf club, you put the ball on the tee, and with your golf club, you hit the ball. The club is in contact with the ball for a fraction of a second. That time of contact multiplied by the force that is imparted on the golf ball, the combination of those two, is what we refer to as the impulse. Okay. Another one, baseball bat. Let's say we're playing baseball. I throw the ball towards you. You're holding the bat. I'm going to give you the example of the bat, the baseball. So let's say, for example, here's the ball moving this way with some initial velocity. Here's the bat. I'm going to call that BC, before collision. Okay, so the ball, let's suppose it has a mass m, initial velocity v, and then there are three pictures here. The second picture is that the bat is momentarily in contact with the ball for a fraction of time. You know what I mean? So in this region right here, the ball is instantaneously flattened. You know what I mean? And so you have that force on the ball due to the bat, action reaction, if you will, this force right here. And for a very short amount of time, a fraction of a second, say 1/10 of a second or even less than that, okay? And as a result of that, what will happen? Well, here is the bat. Now the ball is moving in the opposite direction. Remember, it started going to the right, and now it's moving in the opposite. I'm going to call it V prime. Prime here means after, okay? So let me go back to this, the one in the middle. I call that DC, and this one AC. Before collision, during collision, after collision, okay? These are just my own notation. Of course, nothing happened to the mass of the ball, okay? So how do we define impulse? Impulse, and I think engineers use the symbol J for it, small letter J, I think. J or capital letter I, is basically, in its simplest form, is equal to F times delta T. Okay? The force, let's go back to the DC here. The force here that has been exerted on the ball, if you know what it is, times the time of contact, which is extremely small. And again, if you know what it is. So if you know the time of contact and you know the amount of force that has been imparted on the ball, if you know those two, their product will give you what we call the impulse. Got it? That's basically what it is. Now, there is a better way, impulse. Not better, really. It's just another convenient way of calculating impulse. And that is, if I look at BC and AC. So BC here, if I would calculate the momentum of the ball before it collides with the bat, okay? So the momentum of the ball before, so I'm going to call that B4 or BC. So the momentum here, I'm going to call it P naught. The naught means before, okay? Or initial. So P naught here is going to be MV naught. Is that okay? And then after, which is I am here, so here we have the momentum after, the prime means after. Again, these are all my notation, all right? You're not going to find those abbreviation BC, AC, DC in any book, okay? These are all my notation. Okay, so the P prime here, it would be something like what? It is the mass times velocity, so it's going to be mv prime, correct? But remember, momentum is a vector, and look at it, it's moving to the left, so we have to put that minus sign in there. So it's going to be minus mv prime, okay? So those are the two momenta of the ball before and after, okay? My question is, how the two momenta are related to the impulse? Well, it turned out that that the difference between the two momenta, delta P, okay, is actually also equal to the impulse. Got it? So impulse, J, is equal to the force times delta T. Delta T is the time of contact, which is a very short time, times the force. Or, if you can't find it, okay, basically, if you know what's the speed of the ball before it collides with the bat, the speed of the ball after, if you know those two, of course you know the mass, that's easy, you just put it on a scale and you'll know what the mass is. And so, if you take the two and you get delta P, you will also get the same number here. impulse. All right. So what is delta P? Well, delta P means P prime minus P naught. Is that okay? And P prime is minus MV prime minus MV naught. Got it? Let me just take minus as a common factor. Do you notice something interesting here? Is that a lot of times the delta P here is very deceiving. You may think, oh, it's the difference between the two momenta. Well, yeah, that's correct. But look at that. You're actually adding them up together. Okay? And why would you add them up together? Because the momentum is a vector, and the sign of the vector is important. So that's why we put that minus sign, and you'll end up actually adding them up together. As a matter of fact, most of the time, when you're calculating delta P, the difference between two momenta, initial momentum and final momentum, or something, before or after, a lot of times, you end up actually adding the two rather than, getting the increment, if you will. Okay, that's a little trick that you want to keep paying attention to it. So you don't want to fall into a mistake of taking the difference without paying attention to the vector sign, the sign of the vector. Okay. So anyway, so now we have two equations or formulas that describe impulse. So I'm going to write them all in one single line like this. J is equal to F times delta T, also equal to delta P. Okay, or I can go M V prime minus V naught. That'd be another way of writing it if you want to. So that's basically what impulse is. All right, and again, it is in its simplest form. And we use this formula here, guys, only if the force is a constant. Okay? And why do I say that? Well, if it's a constant and then we have delta T, it's just a number. Okay? For example, I could say the impulse, let's say the force is, say, 10 Newton, and then the time of contact, let's say 0.12 second, whatever, right? So therefore, the J, in this case, the impulse would be F delta T, and that would be 10 times 0.12, and that would be 1.2. Is that right? Did I do it right? 1.2 what? What is the unit here? Well, we have Newton times second, so that's going to be Newton second. You see what I'm saying? Okay, simple, huh? However, sometimes the force here is not necessarily constant, but it's a function of time. Okay, what makes impulse, or the force that is responsible for the impulse, unique, is that the force is a function of time. So let me repeat that again. The force that is responsible for the impulse is a force that is a function of time. This is very important to keep in mind, okay, especially in advanced mechanics. So you have a function. The force is a function that is a function of time, okay? If you go back to the previous lecture, lecture number 8, remember we talked about the force as a function of the position, and this force will produce work, remember? The integral of f of x dx, remember that? x1, x2. We talked about that in lecture 8 and 7 and 8, where when the force is a function of position, and when you integrate it from x1 to x2, that will give you the work done. All right. For example, let me just review this very quickly because it's related to what I'm about to do. Let's say you have Hooke's law, F equals kx, for example. Or you put a minus there if you want to. Okay. Let me write it down better. We have f of x equals minus kx. X here is a variable, so the force obviously here is not a number, it's not a constant, it's a variable, and it gets stronger and stronger with length. The longer you go, the more stretch or more compression on the spring, the larger the force, if you will, right? So the work done to stretch the spring from one distance to another, is, what is it? Just take the integral of that. So it's going to be minus kx dx from some x1 to x2, And of course, we end up getting something like minus 1/2 kx squared from x1 to x2, and then you go on with it, okay? So, and then we call that, what do we call that? Basically the potential energy. You know, the integral of the force will give you the potential energy, okay? So, all of that, we talked about it in the previous lecture. We have something similar here, but again, this force is what we refer to it as, if you remember, we call it the conservative force. Okay, conservative force. And this is a different kind of force. How is it different? Well, it's a function of time. This force depends on time. As time goes by, the force changes. Okay? The force changes here with time. In this respect, we define J, if the force is not constant, just like this one. Okay? J, the impulse, basically is the integral. Now, as I write this, please compare it with this one right here, right? The integral from t1 to t2 of f of t dt. See that? That's impulse. It's not work. Work is a function of displacement x. Okay? This one is a function of time. So the function of time, the integral, will give you the impulse. Okay? Let me explain it very briefly. Let's go to the DC stage right here in the baseball game, right there. This one. Okay? I want to try to draw it to you in slow motion. What's going on here? See, here's the bat. Right? The ball is here. The ball is coming toward the bat. Okay? So what's happening as the ball touches the bat? Here it is. It touches the bat. After a fraction of a second, now it is compressing and compressing and compressing. Okay? It will keep compressing the bat until it is finally, I'm talking about within that fraction of a second, it is flattened like that. I'm going to exaggerate the way it looks. See that? So this compression from here to here, it took time. Remember, it reaches max. This is maximum compression or maximum deformation. Okay. This maximum, and then what happens? Then it bounces back. Okay. So as it bounces back, it will become less flat, less deformed, and then it bounces back in the opposite direction. Got it? How does it look like in a graph? It looks something like this. The force, as you can see here, this force, as it's getting flatter and flatter here, the force is getting stronger and stronger, believe it or not. It's not a constant force. It's going to look something like that. It's kind of a symmetric curve. I'm trying my best to draw it. Where this is, I hope you get the idea. This is the force as a function of time. And this is the time. Okay? And this is where it is completely deformed. The maximum deformation right there. And then, so this part right here, as the ball is coming towards the bat this way, to the left, excuse me, to the right, to the left or the right? To the right, yes, to the right. And then this part right here, as it is bouncing back to the left this way. And both of sides of the curve are symmetric. You know, there's some kind of symmetry to it. You got that? So this is the maximum time. So the time it takes it to time of contact is roughly, you know, this is an asymptotic curve that looks like that, is roughly this one. Okay? This is let's call it delta t, if you will. Okay? This is a very, very important graph. You know what? Let me pause the video. I want to go online. Unfortunately, my ebook is I'm having technical difficulty accessing it, so I need to depend on maybe I'll go to the search engine and find you a graph that looks like that. I'll run back. Here we go. There we go. If you look at this this curve right here, so here is the curve. Here's the time. Look at the time, how small it is in second. 0.00. Excuse me. 0.00. You know, this is like 1,000th of a second, 3,000th of a second, and so on. That in the millisecond, right? 1 millisecond, 3 millisecond, fifth, and up to 7 millisecond. So this is delta t from here to here. It reaches the maximum value of the forces right here, the peak. Here is the force as a function of time, and of course the unit is Newton. And if we draw a line right in the middle from the, this is the peak all the way to the ground level right here, if you will. The line that is in the middle right there, that would be approximately the average value of the force. Here's another one. This is the one that is I've seen it many times. Same thing, right? Also, the area under the curve represent also the impulse. There are other details. You can look them up yourself, and so on. This is the curve when I think of, there we go. I like this curve. This is the one I was looking for. You have the force, and you have the time. There we go. It says here, can I go to that website? Maybe I'll get it bigger. What is that picture? There it is. Let's see. Oh, there we go. Good. Okay, there we go. So that's the curve that I was trying to draw. That was in my head. So the time from here to here is the duration, the time of contact. This is the beginning of the ball touches the the bat. I'm sorry. It touches the bat at this second right here, and then the force gets bigger and bigger and bigger until it reaches a maximum value, and then it bounces back right here. This whole time is in millisecond, if you will. And there we go, okay? And the area here basically tell you the value of the impulse. And what is the area? Well, the area under the curve, which is basically the integral from this point to this point of the function, of this function, if you know the value of that function. Okay, I'm not sure if he has it. There we go. So the impulse I, he uses I, f dt, and if it's a constant, f will be just f delta t if it's a constant. Okay? Okay, good. All right, my curve looks ridiculous compared to what I have just showed you. All right, good. Let me give you an example. So let me give an example and show you how all of that works, okay? Oops. Okay, so suppose we are playing baseball, okay? And let's say the mass of the ball is 150 gram. That's the mass of the baseball. You throw the ball towards me with an initial velocity of 20 meters per second. I'm getting this example from an older textbook that I have here, a hard copy. So you throw the ball towards me with a velocity of 20 meters per second. That's about double that. That's about 40 miles an hour. And then I hit it with my bat, and then it rebounds back towards you with a new velocity. We're going to call it v prime of 40 meters per second. That's about 80 miles an hour. Okay? Also given to us the graph, the following graph. We need to look at the graph and analyze it. It looks something like this. Please note that this triangle, the two sides of the triangle, this part and this part are identical. Okay, they're symmetric, if you know what I mean. Okay, and this is, of course, this is the force as a function of time, and this is the time, and this is the maximum the maximum force right here. I'm going to call it F max, and what else? Okay, also in the graph, it's shown in the graph that the time of contact is 6 milliseconds. Okay? he's asking the question, what is the impulse? Find the impulse J and find the average velocity. See, we're not given the maximum velocity. He wants the average velocity. Excuse me, I'm sorry. Did I say velocity? He's asking what is the average force. In other words, the average, see, remember, the force here is increasing. Started from here, zero force, and then it starts increasing until it reaches a maximum, right? And then it comes down. Okay, so the average force is roughly somewhere in the middle, okay? So he's asking what is the average force? F bar, we're going to call it, not F max, okay? So how do we do something like that? Well, okay, I know that. Let me go back to the formula here. Let me show it to you very quickly, the one I boxed for you. What is it? Right here. So we said that J is equal to delta P. That's really, that's really what counts right here. Remember, it's also J is F delta T. All right? Okay. So let me write it down. So what I have in here is J, since everything is in the X direction, I can write it in the terms of X direction. J sub X equal delta P sub X. It's really not important to do that if you don't want to. But here is the trick. I know that delta P sub X is basically equal to what? Well, it is M, the difference between the two momenta. So it's basically mv prime minus mv naught. Or if you will, mv prime minus v naught. Okay? And then I can just plug it in. So M here, you want to be very careful about the velocities here. See, he didn't give you the sign of the velocity. Of course, it doesn't make sense that both of them would have the same direction, right? One of them is negative, one of them is positive, and that depends on how you set up your baseball game. So let's suppose it's this way. Okay, so this is V naught. And then, so V prime would be this way. You can do it the other way around if you want. Here is the bat, and here is the ball, V naught, and then this would be V prime. It really doesn't matter. You'll end up getting the same answer, okay? So I'm going to set it up with this one right here because that's the one I'm used to. Okay, so in this case, I will have, this is V prime right there. So we would have here V prime, which is minus 40 minus 20, and that will give me, times, I'm sorry, I forgot to put the mass of the, which is 0.15, correct? Kilogram. Remember, the mass here is 150 gram, which is 0.15 kilogram. And when I calculate all that, so it's going to be here 0.15 times minus 60, and then the minus here basically gives me a negative 9 kilogram meter per second. I forgot to mention the unit of the momentum. Remember, the momentum is what? Any basic momentum is mv, so the unit would be kilogram meters per second, and that's basically the unit of momentum. Okay, make sure you know that. So. And there we go. I have delta P sub X, if you will. Okay. Again, the minus sign here does not make much. It's not important because, like I said, it depends on your orientation of the baseball game that you're playing. If you do it the other way around, you'll end up getting a positive. So we can basically safely ignore that minus sign. Okay. So let me just say that delta P here is equal to 9 kilogram meter per second. I hope you believe that. I hope you understand why the minus sign is not important. Okay, so I got the momentum. Now he's asking me to find the impulse. Well, I know that impulse is equal to delta P, so there we go. I know what impulse is. Easy. So the impulse, but J sub X, if you will, remember impulse is also a vector quantity, is equal to delta P sub X. So therefore, J sub X is equal to 9 kilogram meter per second. It has another unit. What is it? Newton second. It's the same thing. If you analyze it, you'll get the same thing. So either or. So there we go. I got the impulse. He's asking for that. I found it. Now, how do I find F average? Well, generally speaking, okay, F average is the impulse. If you look at it this way, remember F average is a number. It's not a function. F average is a number. Okay, it's not a function. And we know that if it's a function, then the formula J equals F delta T. And this F here is a bar, because it's a number. Remember, average is not a function. You can't have a function as an average, because average is just a number. Okay, so I can find it easily, because delta T is given to me right here. That is 6 milliseconds. So I can just go back and get that average. Remember, this average, guys, F bar, is not F max. F average is right here. Let me draw it for you. It's right here. Somewhere right in the middle. Okay, the average value. You got it? Average value. There it is. So this number right here. Okay, how do I find this number? Well, you go back to this simple formula. J equals that. So F average, F bar, would be basically J sub x over delta T. I found J sub x right here. And delta T is given to me in the graph. So it's going to be 9 divided by, I forgot what the number is, 6 millisecond. So that's going to be 6 times 10 to the negative 3 second. This is Newton second. So by canceling the second, you'll end up with a Newton, and that will give me 1,500 Newton F average. There we go. Got it? Simple? Okay. Now, here is a trivia question for you. Well, not a trivia really, but an extra question. Suppose as I go back to the problem, he said find the impulse and F average. Suppose also he's asking me to find what is F max. I'm talking this number right here. How would I find that? Okay. Again, this is also a number. I mean, the F that is a function of time is that variable that is causing it to go this way. But that's also a number. How do I find that? Well, generally speaking, okay, if you're stuck and you are in a hurry, it's roughly about double the average, roughly, because it's around the middle. So again, this is not terribly accurate, but it is a good guess. It's around there. So expect it to be the F average. We got the F average to be 1,500, so I am expecting it to be give or take 3,000. Okay, give or take. Okay, but how do I find it? Well, let's go back to the graph. Let me make the graph again. The graph looks something like this. It's a triangle. Remember, we said that impulse, J, is equal to the integral of f dt, correct? And what did we say about this f dt? Well, what we said about it is that f dt is nothing but, from a calculus perspective, it's the area under the curve. In other words, it's the area of the triangle. Isn't that interesting? It's the area of the triangle. I mean, I may not be able to, I'm going to have difficulty integrating a triangle like that, you know, but I know that whatever integral that I'm going to get, it's going to be exactly equal to the area of the triangle. Well, let's see, the area of the triangle. Well, what is the area of the triangle? What's the area of a triangle? The area of a triangle is half the base times, can I go a little bit further? Let me make it this a little bit bigger, times the height, right? The base is right here, 6 millisecond. And what's the height? Well, the height from here to here. What is that? Well, that's F max. Isn't that cool? Make sense? Here, go back to the graph. Right here. The height is right here. If I can draw a vertical line, there we go. And this height is nothing but F max. This is the height. And that's the base. So now, going back to my formula here, J equals to half the base times the height. See the trick? So half, the base is 6 milliseconds right there. So that's 0.006, is that right? 0.006 should be 0.006. What's the height? F sub max. And that's what I want to find. And what is J? Well, J, I got it long time ago, right here, equal to 9, because delta P is 9. I go back and just plug it in there, and voila, I got V max, F sub max. I keep saying V, sorry. So I have F max is equal to 2 times 9 divided by 0.006. Again, it should be close to 3,000. Keep that in mind. When you take an average of value of something with a peak, usually it's around half of it, roughly, give or take, if it's symmetric, okay? There's not a rule. Anyway, we have 18 divided by 0.006, answer 3,000 exactly, actually. So we have 3,000 Newton. And there we go. That's a cool problem. I hope you enjoyed it. Okay, let's do another one. Again, it has to do with impulse. Okay, the next problem or example is called the bouncing ball. Very interesting example. Before you do it, you can, before you watch this example with me, if you want to, if you have a ball, any ball that you have at home, grab it right now, maybe pause the video, grab the ball, say you have a golf ball, baseball is not interesting, ping pong ball, racket ball, lacrosse ball, or even a soccer ball or a basketball. Anyway, take it, hold it with your hand, say up to the level of your chest, and then let it go. It will fall, hit the floor, bounces back, but it will never come back to the level of your hand, okay? It will always be a little bit less, okay? This is something called coefficient of restitution. You can look it up if you want to, but it's not, we're not covering it in this course. But there is some loss of energy, okay? But the question is, using the concept of impulse, I want to know the new height. In other words, here is the example. So I find this example is kind of one of my favorite examples, but hey, I'm a geek. Let's say here is the wall, or your height, let's say. So here is the ball, whatever ball you're using, racket ball or something. And you're holding it, and the initial velocity of the ball is 0, right? And then you let go, so it falls. It hits the floor. Let's say this is the ball right before it hit the floor. I'm going to call that V, okay? Then it hits the floor, okay? Then it bounces back. I'm going to draw it here as it bounced back, okay? But it's going to be on the same line, but I'm going to draw it here just for clarity. So now when it bounces back, here it is, bouncing back. So this velocity is the velocity of the ball just before it hit the floor. Keep that in mind, okay? This one, after it hit the floor and bounced back, okay? So we're going to call that V prime. This one is, we're just going to call it V for the lack of a better one. And then what's going to happen to it is going to go up, 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 and then it's going to stop some point here, okay? And of course, it's going to stop, so that's going to be V equals 0, and that's the new height. We're going to call that H prime. Okay, and of course, we're starting with H naught. The question is, what is H prime? Given the following, okay, what's given to us? Okay, we have the mass of the ball is 100 gram, all right? The height H naught is 2 meters, all right? So that may be taller than your height. 2 meters, that's about, yeah, a little bit taller than me, I guess. I am 1.82 meters. And then, so we are asked to find what is H prime, okay? So how do we do this problem? I think, oh, one more thing that is given to us. I'm sorry, I'm saying this problem from memory. What's given to us is the following diagram. It's not just this diagram. There is a graph that is given to us. So we have a graph, X and Y, like this, or should I say F and T, and we have this triangle again. But this time it's a little bit thinner. Again, symmetric on both sides, okay? This side and this side are symmetric. I'm just not able to do it. And then given that this is 300 Newton, and the time of contact of the ball with the floor is 8 milliseconds. Okay? That's given to us. All of that is given to us. So let me recap, make sure that I understand we understand what the problem is asking for. Okay, so we have a ball. I'm holding it between my hand at 2 meters height. The ball is 100 gram, all right? That's about 0.1 kilogram, very light. Let go, the ball falls, bounces back, and it reaches a different height, a lower height, that is, H prime. We're starting with H naught. H naught is given to us, 2 meters. We're given to us, so we want to find the H prime. Now, also given to us is that when the ball hits the floor, the force here is not constant, keeps, you know, as time goes by within this 8 millisecond, fraction of a second here, the force keeps getting stronger and stronger. It reaches a maximum value of 300 Newton, okay? And then it bounces back, okay? So that's the information that we have. So how do we do this problem? Okay. In order for me to know V prime, see, I need to find H prime, but I want to find what V prime is, and this V as well. So I have to know those two before I work on the H prime here. So this V right here, how would I find it? Well, again, you can go back to the previous lecture where we covered conservation of energy, or you can use kinematics. So if I use kinematics here for the first stage, okay, I'm going to call this stage number 1. I'm going to call this stage number 1. And this one here, stage number 2. These are not very pretty. Let me go put them here. How about if I put them in a different color so you see them? Put it in red. So this is stage number 1 right here. And this is stage number 2. You know, the bounce back. Okay, so let's talk about stage number 1. I want to find V, this V right here. Why do I find it? Well, because I need to find V prime. I can't find V prime without V. And if I find V prime, I can find, hopefully, H prime. Okay? So, let me find V. I use kinematics. And again, I'm going to use the second equation, this one. V squared equals V naught squared minus 2GH h naught, right? Kinematic 2. This is 0, right? Because the initial velocity is 0. The height here is negative, so that's going to be a negative. So there will be a negative here, and negative here going to be positive. So let me just, this is just, I don't need this minus sign for now. You got that? Remember, h naught here is a negative number. It's basically minus 2. If I put it in here with this minus, it's going to be positive. So I'm just going to put it like that. I want to write everything symbolically for now. So in this case, v, which is the velocity of the ball just before it hit the ground, is basically that. Here it is. Okay, right here. The velocity of the ball just before it hit the ground. Okay, cool. Now, what I want to do now, I want to find an expression for v prime. Notice here that this v is linked with the height. So I can find a link between v prime and h prime using the same kinematic equation. I hope you believe that. Here it is how. Now let's look at stage number 2. We're going to do it in reverse. So we started with some initial velocity. Remember, the moment it bounces back, it's v prime, and it goes up until it stops. So that's a deceleration process. So I'm going to use the same equation where h here is h prime. Okay? And this is the initial velocity. So I'm going to write down the same formula, this formula, except with my notation for stage 2. So it becomes v squared, which is the final velocity right here, guys, equals to v prime squared plus, again, I'm ignoring those minus signs, plus 2gh prime. This one is 0. Okay? You know what? I'll put it that minus because I'm going to move this to the other side. It's going to be negative. So let me take that minus. So in this case, v prime is equal to square root of 2gh prime. There we go. I have an expression. Again, I still don't know what v prime is and what h prime is. I don't know. I can get a number out of that. No problem. I have everything. I mean, I know g 9.8 and h 9 is 2 meters, so I can get a number out of that. No problem. Here, however, I have two unknowns, v prime and h prime. But I know I'm in the right direction. Okay, I'm putting in my formulas for now. I'm building up formulas. Hopefully, I will be able to link them all together. What else I can do? Well, let me go back to the graph. Remember, I got those two formulas from this diagram, the one I created. Now, this graph is given to me. What can I get out of it? Well, I have a triangle. So if I take the area of the triangle, which I know I can find, I can get the impulse. Aha. Okay, so the impulse, let me put it in, go back to black color. So find impulse from graph. Well, J is equal to, it's delta P, which is M v prime minus v, if you will, correct? I can put it in there, so it's going to be m, again, as a number, it's given to me. V prime is this thing here, and this one, and v is this one. So I can plug him in there. Square root of 2gh prime minus square root of 2gh naught. Okay, and that's equal to j, all right? Do you see where I'm going with this? See, this is all known to me. H naught, I know what H naught, I know what G is, I know what M is. So the only unknown on this side is H prime. Make sense? So, but I can find J. How? Well, J is the area under the curve. Basically the area of the triangle. And once I do that, I'm done with the problem. You see the plan? Okay, good. So here we have J, but J is area of the triangle. Oops, triangle. Triangle. Did I spell it right? Triangle. go. Sorry, there we go. So we have here J is equal to half the base, which is, let me call it delta T, times the height, which is F max. All of that is given to me. So it's going to be half. Delta is 0.008 second, right? Multiply that by the F max, what is it, 300? 300 Newton. And then I can calculate all of that. And that will give me, let me calculate that. I hope you're calculating things with me. So it's going to be 0.008 times 0.5 times 300. Answer, 1.2. Okay, so we have the impulse is 1.2 Newton second, or 1.2 kilogram meter per second. They're both equivalent. And now I can come back, I can take this thing and put it right here, and then I would do my algebra to find h prime, and I'm done with the problem. Okay, so let's do that. So plug back, let me call that equation, let me call it star. So plug back into star. So I have here J, again I'm reading it from here, J is 1.2, equal, the mass is 100 grams, so that's 0.1, times square root of 2gh prime, okay? I don't know the h prime, minus 2gh naught. Now, if you do it on the side, I have it, I've done it already in my notes here. It's equal to, if you do it on the side, you will get 6 point, I'm sorry, I don't know it. Hold on. So let's calculate that. So it's going to be 2 times 9.8 times, what is it, 2, and take the square root of that. Answer 6.26. So we have here 6.26. Just like that. And then we do the algebra. I hope you know how to do that. And we get h prime. And h prime in this case, it would be equal to, let me just give you the answer. If I did it correctly, I remember doing it last year in class, is equal to 1.68 meters. Make sure that you check my work. Now, if you are curious to know what is the velocity of the ball as it bounces right here, well, here you go. They use this formula right here. V prime equals square root of 2gh prime, and you already know what h prime is right here. And when you do that, you can actually find v prime to be equal to 5.74. Again, I'm copying this from my notes. 5.74 meter per second. Okay? Okay, good. All right, now let's do some collision problem. That's basically what you need to know for as far as impulse is concerned. It's a big subject, but for the level of the course that we're teaching here, this is probably what you need to know. Now I'm going to move on to the collision problems, which you have to use momentum. Collision. Before I do collision problem, there is a very important conservation law called conservation of momentum. We already studied conservation of energy, and we said that the conservation of energy basically says the total energy is equal to K plus U, or V, okay? Where the kinetic K here is the kinetic energy, and then this one is the potential energy. In other words, the sum of the kinetic plus the potential is always equal to a constant number, equals constant number value. Okay, that's the conservation of the conservation of energy. Conservation of energy. There are a lot of conservation laws in physics: conservation of energy, conservation of momentum, conservation of angular momentum, conservation of charge, conservation of baryon number, and so on. There are so many different ones, okay? So, what is the conservation of momentum? Again, I'm going to explain it to you through an example. Suppose there are 2 billiard balls, all right, or 2 balls moving in the opposite direction, and they are about to collide with each other. So this is mass m1 moving with velocity v01, okay? This one, mass m2, moving with initial velocity v02, okay? So this is what I call BC, before collision, all right? So think of them like 2 billiard balls. They come in, they hit each other, and they bounce back. So let's draw AC after collision. So here's ball 2 moving in the opposite direction with a new velocity. I'm going to call it v prime 2, okay? Of course, nothing happened to the mass. I hope not, okay? And then we have ball 1 moving in the opposite direction with velocity v1. Suppose, I mean, not necessarily moving the opposite direction. They could be depending on the mass. But let's just suppose that this is the scenario, all right? So this is M1 right here, okay? Now, what I want to do is I want to calculate the momentum of each ball before and after collision, that is, all right? So if I look at ball number 1 before collision, so what is its momentum? I'm going to call it P01, okay? P01. And that P01 is equal to what? Well, it's going to be equal to M1 V01, right? Again, remember, this is a momentum, so the direction is important. The ball 1 is moving to the right, so it's positive, so there's no problem here. Now, if I want to calculate the momentum of ball 2 before collision, so that's just going to be P02 equals to what? Well, it's moving to the left, so that's negative. So that's going to be negative. Did you hear my cat? I don't know why it's meowing. V02. Nope, V02. See, I can't write 2 because my cat's behind me meowing. I have no idea what they're doing. Hello? Right back. Okay, so those are the 2 momenta of the 2 balls before collision, all right? Now, let's write the same 2 momenta for the 2 balls after collision, okay? So here we have P prime 1 is equal to what? Minus M1 V1 prime, and P prime 2 is equal to M2 V prime 2. Got it so far? Okay, what I want to do now, okay? What I want to do, I want to add up the 2 momenta before collision. I'm going to add them up together, okay? And I'm going to add up the 2 momenta after collision, like this. P01 plus P02. And also I'm going to add up, so here we go, I'm going to add them up. And then I'm going to add them up, there's no need for that. And then I'm going to add them up here, so it's going to be something like P prime 1 plus P prime 2, okay? And what I will notice that the sum of the momenta, listen to this is very important. The sum of the momenta before collision, right here, is always equal to the sum of the momenta after collision. That's the law of conservation of momentum. Extremely important law, very fundamental law in physics. Okay, actually, if you want to memorize it, here is how I memorize it mathematically. Sum of the momenta before, sum of the momenta after. Please write this one down somewhere on the wall or in the bathroom or whatever, and keep it handy and memorize it forever. That's the law of conservation of momentum. the sigma p naught, the sum of the momenta before, here they are, equal to the sum of the momenta after. Got it? Okay. Or we can write it, explicitly. So we can just say m1 v naught 1 minus m naught v naught 2 equals to minus m1 v1 prime plus m2 v2 prime. And there we go. That's another way of writing it. And so on. You got that? Okay. I'm going to give you a bunch of examples and show you how to apply it. But for the time, let me just move on to something else. I want to finish all the topics and then we'll do examples or problems. There are two types of collision. I mean, there are several, but we're just going to be studying two types of collisions. Two types of collisions. One is called elastic collision. And the other one is called inelastic. Okay, now elastic collision, let me just begin with elastic. I mean, most collisions in the real world, they are neither elastic nor inelastic. They're actually somewhere in the middle, but you have to take into account something called the coefficient of restitution. Okay, but those are the two extremes, really, the elastic and inelastic. Anyway, so what is elastic collision? The easiest way to think about it or to picture it is like when you're playing billiard ball, pool. Okay, so what happens? The two balls bounce against each other and they move off without sticking with each other. Okay, that's an example of elastic. They basically they bounce off and they don't stick together. Okay, that's in the simplest. If you want to explain it to a high school kid, that's basically how you would explain it, because they don't stick together after collision. Inelastic, however, they actually stick together after collision. An example of that would be car collision. When you have two cars colliding with each other, most likely they will stick to each other, at least for the first fraction of a second. They're sticking together and they're moving off with one common velocity. That's an example of an inelastic collision. Okay, but there is more to it than just basically bouncing off elastically. Okay, elastic collision basically says the following: is that the conservation of momentum holds. So sigma p naught equals sigma p prime. Okay, that's the first rule. Also, the total kinetic energy before collision is equal to the total kinetic energy after. And listen what I said. I didn't say the total energy. I didn't say the total energy, this one. I said total kinetic energy. Okay, that's not a conservation law. In other words, let me go back to this picture right here. The picture of the two billiard balls colliding, right? If I would add up the kinetic energy before and after of each of them and add them up together, what I will discover is that the sum of the kinetic energy before collision, the sum of the kinetic energy before collision is equal to the sum of the kinetic energy after. Okay? That's what makes it elastic. This is very important. Got it? In other words, if I go back to the same picture, let me go back to the picture again. I want to put a different color because this is very important that you have to make sure you understand that. So in addition to what we're doing here, oops, what did I do? I think I put something, oh, okay. So in addition to the momentum here, okay, we have something else, is that if I would calculate the kinetic energy here, whoops, what am I doing here? I need to fix that. I'll run back. So what I'm trying to say is this. So if I look at the two balls colliding here, I can say that here, right here. So I can say that the kinetic energy of the first ball added to the kinetic energy of the second ball, remember there is no, because the kinetic energy is a scalar quantity, direction is not important, must equal to the kinetic energy of the first ball after collision plus the kinetic energy of the second ball after collision. There we go, okay? This is not the conservation. That's just basically the sum of the kinetic energy before and after are equal. And that's a characteristic of elastic collision. You're not going to find that for inelastic collision, okay? So that's basically what elastic collision is. You have two rules here. The first one, conservation of momentum, holds. Okay, some of the momentum before and after are equal. Also, some of the kinetic energy before and after are equal. Got it? Okay. Now, for inelastic collision, the conservation of momentum still holds. So basically, this formula holds fine, no problem. Okay, so the sum of the momentum before of the momentum before collision is equal to the sum of the momentum after collision. However, the sum of the kinetic energy before does not equal to the sum of the kinetic energy after. Okay, so basically, you don't use this rule for inelastic collision. That's what I'm trying to say. You do not use it. So this one does not hold. Why is that? Because they stick together after collision, and a lot of this kinetic energy is lost. Okay? So basically, part of the kinetic energy, the reason is because part of the kinetic energy is lost to, say, sound, is lost to, say, heat, sound, vibration, and so on. Okay? Okay, that's basically what we need to know. All right, those are the rules that I wanted to show you. So let me do a bunch of problems. I have at least 4 or 5 problems to work on for this chapter. Okay. I begin with a simple example. It's an example of inelastic collision. Imagine you have 2 gliders, all right? Think of it like a hockey pucks, okay? 2 gliders that are, you know, like a air hockey game. So you have those 2 pucks, they're easy to slide on the surface. So we have 2 gliders. Here's one. Glider number 1 moving in this direction, and glider number 2 moving in the opposite direction. They're both on the same surface. Okay. This one has a velocity, glider number 2 has a velocity v naught 2, and velocity of the glider number 1 is v naught 1. The mass m1, mass m2, this is all BC, right? Before collision. And then AC, what happens is that both gliders stick together and they move off with one single it's called common velocity, big V I like to call it, big V, like that, okay? That's the story. Now he's asking for the, well, okay, so what's given to us? Given the mass of glider 1 is equal to 200 gram, mass of glider 2 is equal to 400 gram, the velocity, initial velocity of glider 1 is equal to 3 meters per second, and we are asked to find what is the initial velocity of glider number 2. Okay? Oh, and the common velocity, which is the velocity of the 2 bodies after they stick together, this big V, is equal to 0.4. Okay? So I hope this is an easy problem for you. Very easy. All I need to do is to appeal to the law of conservation of momentum. You see what I'm saying? So conservation of momentum basically said sum of the momenta before equals sum of the momenta after. Now I'm going to write them down and paying attention to the vectors, to the direction of the signs of the vector. So here I have m1 v01 minus m2 v02 equals to, well, what's equal to? Well, it's moving to the left, so that's going to be minus. And then they stick together, so we have one combined mass, m1 plus m2, times big V, one combined velocity as well. I call it, again, we call it common velocity or combined velocity. Okay, and there we go. And all I need to do is plug in the numbers and then solve for v02 and you'll be done. So let me plug it in. So I have here m1 is equal to 200, which is 0.2. 0.2 kilogram. V02 is equal to 3, V01, excuse me, minus 0.4 V02 equals to minus 0.2 plus 0.4 times 0.4 here. And then we work it out, should be easy. So V02 is equal to negative 2.1 meter per second. Does the negative sign make sense? And I hope it makes sense because look at that. This is going this direction, so it's going to be minus. Got it? Okay. All right, one more. Another problem, this is an example from the book, it's called a ballistic pendulum. This is how people back in the early 20th century were able to to measure the speed of a bullet by using the ballistic pendulum. And there is also a lab that you're going to be using where you're going to be working on, you're not going to be measuring the speed of a bullet, but something else. Example, ballistic pendulum. Okay. So what you have in a ballistic pendulum is basically you have this is the ceiling, that's a cable, and maybe a couple of cables maybe. And then we have a block of wood is hanging there. It's not swinging or anything. The length of the cable is 1.5 meters. Again, it's given to us. And then we have the this is the hold on. I'm a little bit ahead of myself. Sorry. So let me just show you the diagram, or the apparatus. So basically, you have here's the ceiling, here's the cable. We have a block of wood right here, and then at some distance here, you shoot a bullet that you would like to know its speed. The bullet goes with some unknown speed. We're going to call it V0. Okay. Now I know the mass of the bullet as well. Okay, so I know this information. I'm going to call it M sub B. B here is small b for a bullet. Okay. So what's going to happen when the bullet hits the pendulum or the block? Okay, we're going to assume that the block is so big, the bullet is not going to penetrate it, come out from the other side. We're just going to assume that. All right. So what's going to happen here is that we have two more stages here. The second stage that I'm going to draw is that the moment the bullet enters the pendulum or the block, here is the bullet. Okay, right there, right at the moment, maybe just right when it enters it, right here, maybe. Okay. And the third stage is this. So what's going to happen? The bullet block system will rise up. It's going to swing up before it comes back and swings. So it's going to swing up to some maximum distance. It's going to look something like that. So let's say this is the original height right here. So what's going to happen, I'm going to try to draw it as much as I can, as good as I can. It's going to look something like that, where the block now is here. Again, I'm exaggerating the way it looks. And now the bullet has penetrated, and it's right now it's lodged in here. Here is the bullet. Okay? So it has risen up a distance or a height h. By measuring this height, which we can do in the lab, I can find the speed of the bullet here. Can you believe it? I'm going to show you how. Okay? All right, let's look at the data. So the data that is given to us, let me just write them down. The length of the cable here is 1.5. Okay, the mass of the big bullet, excuse me, the big, the block, I wanted to say. The mass of the block is 1.2 kilograms. The mass of the bullet, m sub small b, is it's 100 gram. That's a pretty thick one. Anyway, 0.01 kilogram. That's a very heavy bullet. 0.01. Of course, we are trying to find the initial velocity of the bullet, right? And we don't know the height here, and that's about it. Okay? So how do we do this problem? Okay. We want to appeal to conservation of energy and conservation of momentum. Let me start with conservation of momentum. And I want to start with conservation of momentum between this stage here and this stage here. The first stage and the second stage. Now, what is the second stage? The second stage is basically the moment, not momentum, the moment the bullet enters the block. And both of them are about to move with one common velocity. So they have a common velocity right now, right here. Big V. See what I'm saying? Of course, as they go up, they're going to stop right here. There is no velocity here. Okay? So what's going on here in terms of momentum? Okay, I mean, I'm not talking about the velocity here. I'm talking about the momentum of the bullet here. With the momentum, a lot of that momentum is being transferred to the block, and that's why the block moved up. So part of that momentum is being transferred to the wood. So that is conservation. So the total momentum here for the bullet is equal to the momentum distributed here. So I'm going to write it down, the momentum equation. So I'm going to have here m bullet v naught equals to, remember I'm here. Well, here we have an example of inelastic collision because the bullet and the block are embedded. So it's going to be the mass of the bullet plus the mass of the block, and they're both moving with one big common speed v. Okay? And there we go. I'm going to box this equation. I'll come back to it in a minute. Okay? Now, what I want to do now, I want to take the stage, I'm going to take the stage 2 with stage 3. And I'm going to use conservation of energy. So what's happening here is that the moment the bullet enters the block, now the block and the momentum and the bullet are moving with one common speed, big V. There is no height going on here. So all of that is just kinetic energy equal to this V, velocity here. And then this kinetic energy converts into potential because the block stops here at the height. Make sense? So, in other words, if I use the conservation of energy here, in stage 2 is basically kinetic plus potential, but there is no potential because potential is what? Height. There's no height here. So that's 0. So I have basically the E equals to 1/2 mv squared. M here is the mass of the block bullet system. mv plus m big V, V squared. There we go. That's the energy. And that's it. Now here, however, there is no kinetic, because all that kinetic energy has been converted into potential to rise or to lift the bullet block system up to a height h. So that's equal to the total energy here is K plus U, but K is 0 because it stopped. Okay, it reached a maximum height. So all of it is just basically mgh for U here. So that's going to be m sub b plus m sub big V g h. Got it? And those two quantities must be equal by the conservation law. So now I have another equation beside the momentum equation, and that's equal to 1/2 m sub b plus m sub big V v squared equals m sub b plus m sub big V sub gh, and the masses cancel out, which is nice. Again, I'm not interested in this common velocity, so I'm going to solve for it and eliminate it here, and then I'm done with the problem, so I can solve for V naught. So let me solve, solve for V, big V that is, and that's going to be 2gh under the square root, and that's the common velocity. I'm going to take that and put it right there. So, and then with one step, I can solve for V naught. Move m sub b to the other side. So I'm going to get something like this. M sub b plus m sub big V over m sub b times big V, which is basically square root of 2gh. And there we go. Oops. Okay, so that's it. Well, this is the end of the problem. So let me just recap very quickly. Remember, this is a problem that you would do in the lab for a bullet. You don't do a bullet. You basically have a ball with a spring, and then you hit it, and then the ball latches to the pendulum, and it moves up a little bit. Okay, and then you will be able to measure the height from here, and that's why you can get this number right here, the height here, from the lab. Okay, so you can think of it like the height is given to you, or if you will, measurable. You can actually measure it in the lab. Okay, and then from this information you would find the velocity of the ball, or the bullet for this matter, whatever it is. Okay, I hope this is clear, and then we can just plug in the numbers. I have all the numbers that we have. We have the length of the pendulum we don't need if you are given the height here. And the masses, the rest is just masses. I got the masses here. Okay. Now, what if you are not given the, if you're not given the height, but given the length? Well, you need also the angle here. And there is a relationship that links the height with the length. And it's a relationship, you may want to write it down. The height is equal to the length times 1 minus cosine theta. Very famous relationship that links the height of the pendulum, if you will. Whoops. That links the height of the pendulum, this height, with the length of this is the length right here. Okay? But also given that you have to know the angle here. Okay, that's cosine theta. Okay? Anyway, there we go. Okay, one more. Okay, next. This one a little bit more sophisticated. What you have in here, you have two blocks, if you will. Here is the surface. And I have a block here, block number 1, and then block number 2. Now, block number 2, they're both sliding and coming towards each other. Block number 2 has a spring attached to it like that, okay? With stiffness constant K. both again coming toward each other like that. So this is V01, this is V02, and let me write down the data. So M1, the mass of block 1, is equal to 1.6 kilogram. That's pretty heavy block. Mass of block 2 is heavier, 2.1 kilogram. The stiffness constant, or the spring constant, is 600 Newton per meter. Is that right? Yeah. And the initial velocity of block 1 is 4 meters per second, and the initial velocity of block 2 is 2.5 meters per second. Okay, there we go. And the so basically it says block 1 moves with V1, and then block 2 is moving with that. You have spring attached. The question is, he said, find the velocity of the two blocks after collision. So basically find V1 prime and V2 prime. Basically that's what the question is. Okay, so again, this is an example of inelastic collision. I'm sorry, this is elastic collision because they don't stick together after collision. They bounce back. Okay, so let me write down the momentum equation. Remember, momentum conservation holds whether elastic or inelastic, and this is an example of elastic collision because they don't stick together, therefore the kinetic energy is also conserved, right? Okay, so what we have in here is the sum of the momenta before equal to the sum of the momenta after, right? So here we have M1 V01 minus M2 V02. Let me just put them in formal definition of it. Equals to M1 V1 prime plus M2 V2 prime. Okay, and there we go. Now there is a formal way of solving. See, if you put in the numbers, let me put in the numbers. So if you put in the numbers, you're going to get here 1.6 V01 is 4 plus 2.1 times 2.5, is that right? Equals to M1 is 1.6 times V1 prime plus M2 is 2.1 times V2 prime. As you can see here, you have one equation with two unknowns. You can't do it. You see what I'm saying? Now, there is a shorthand way of solving those kind of problems. Again, if you look up your book, you will find them. And let me try to find them for you on the web. It will save you a lot of time rather than doing the calculation here. If you go to Hyperphysics, and I think I told you in a previous lecture, it's one of my favorite websites for physics. You find just about anything you want to look up in as far as your physics courses are concerned. Anyway, I just looked it up. This is Hyperphysics right here. I highly recommend this website. It's a wonderful website for undergraduate physics. Anyway, so they have all different formulas. Elastic collision where target is at rest. We haven't done that. But with what we're doing here is that we have, going back to our example, we have both of them moving toward each other, as you can see. So both of them are moving, and if they both are moving, we're going to use this one right here. So this is the mass M1 and M2, and then this is his notation. When you have V1, it is equivalent to V01 right here. You get that? That's V1, and V2 is V02 right there. Okay. So all you need to do, you plug in your numbers there, and immediately it will give you the velocity of those particles. Of those two blocks after the collision. You see what I'm saying? And once you do that, you can just pause the video and look at them, and then you can just put them in there, and that's it. There is also different cases. You have velocity after collision, where this is the head-on collision where the target is at rest, and then we have this formula and so on. You can read this page. Again, you can just look it up from there. You can go back and look at that page. But that's probably the most important one here, because even if the target at rest, then you can just let V2 equals 0, you'll end up with this formula right here. And that's basically what you got somewhere there, right here. This basically by letting one of them to be 0, this one 0. And we get that and this one right there. Okay? All right. So all you need to do in this case, simply plug in those numbers in there, and that will give you the answer. So let me just write it down, and I'm gonna just follow how I did it in my handout here. So I will have the following: V01 minus V02 is equal to minus V1 prime minus V2 prime. This is another version for it here. And then once we get this, we get V2 prime equals to 2m1 V01 plus m2 minus m1 V02, all of that equal to, or maybe just equal to m1 plus m2 over m1 excuse me, plus m2. And I think it looks the same as the one in hyperphysics. Let me show it to you right here. I'm trying to squeeze them both on the same page so you can see them. That's not going to work. There we go. There we go. So here we go. So we have here 2m1 over the sum. Here it is, V01 plus, I didn't pay attention, I already took care of the minus sign at the top. And then we have here m2 minus m1, m1 minus m2, and that's why you get that minus sign, right? And then divided by the sum times V01. So it's basically the same formula. I hope this is clear for you. And then you just plug in your numbers in there. And once you plug the numbers, you're going to get V2 prime is equal to 3.12 meter per second. And we do the same thing for V1 prime. Again, you go back to that formula in hyperphysics and you plug it in, and then you'll end up with negative 3.38 meter per second. And there we go. Okay, I hope this is clear. When it comes to inelastic, it's usually easier to deal with, but for elastic collision, I would recommend that you keep those formulas handy, specifically this formula right here. Okay, just write them down and keep it handy. So whenever for whatever problem that you're working on. Okay, good. Let me do a problem from the book. Again, we don't have the book. I'm just going to read to you the problem. Number 45. Okay, the problem says, I'm just going to read it for you. Unfortunately, like I said, I can't access the book. It says, a package of mass M is released from rest at a warehouse loading dock and slides down 3 meters on a frictionless chute. Okay, so what you have, let me draw the picture. There is a picture in the book about it. So you have a track or a chute that looks something like that. And here is the package. It has a certain height, 3 meters, to the ground. There is the ground right here. This is 3 meters. Whoops. H equals 3 meters. The mass M, he said it's released from rest, so that means V0 is 0. And so it slides down the chute here, just like that, okay? So let me repeat the statement. A package of mass m, right there, is released from rest and warehouse dock and slides 3 meters high, frictionless chute, blah, blah, blah. Okay, to a waiting truck. Unfortunately, the truck driver went on a break without having removed a previous package of mass 2m from the bottom of the chute. So here what you have on the other side right here, we have a bigger block or package here of mass 2m. Okay, this is mass m, this is mass 2m at the bottom of the chute. Now, we have two parts, part A and part B. Part A says, suppose the packages stick together after collision. What's their common velocity after collision? So we have, suppose they stick together. That means we have an example of inelastic collision. That's a collision. And we are asked to find what is big V, the common velocity after collision. You see what I'm saying? Okay. So what I want to do here, again, it's a combination of using conservation of energy and conservation of momentum. Why do I need to use conservation of energy? Because I'm given that this package right here has initial velocity v. It slides down 3 meters. I want to know the velocity of it right before it hit package number 2. So what I'm going to do, I need to find the velocity here. So what I'm going to do, I'm going to use conservation of energy. Okay. So here, because the conservation of energy tells me that the total energy here is basically potential, mgh, right? And here, well, there is no height here. It's all kinetic. So all that potential here became kinetic. So I need to find V naught for M package BC before collision. Got it? So how do I do that? Well, I use conservation of energy. The total energy here is nothing but potential, mgh, and the total energy here is all kinetic because there's no height there. It's equal to 1/2 mv naught squared, or maybe just call it v1 squared, or what should I call it? I'm just going to call it v squared. Okay. Again, what I'm trying to tell you is that the velocity right before collision, right here. Okay, this is the package m right here. Now it's here, and it's going with a velocity v. Okay, so I can find it. So the masses cancel out. So the v is basically 2gh, and I can just plug in the numbers. So it's going to be 2 times 9.8 times 3, and that will give me 7.67 meters per second. So that's the velocity before collision. Now, I want to know what is the common velocity. In other words, if I draw a picture, this is BC right here, right? AC is going to look something like that. We have one big mass. This is M, and this is 2M. Here's the track, and it's moving with one big V right there. Okay? So what do I have in here? Let's start that. This is AC. BC is basically what I have drawn here. It looks something like that. Here is V, package number 1, moving with velocity V, the one I just calculated. And then we have 2M is just sitting there, sitting duck. It's not doing anything. It's not, that's 2M. Okay, but the velocity of it is what? 0 here. Okay, so by using conservation of momentum, so I have here sum of the momenta before equals sum of the momenta after. Well, before is just mv. After is right here. It's what? M, here that you have a total 3m, big V. The mass cancel out, and therefore the big V is basically 1/3 of the velocity that So it's going to be a third of 7.67, and that would give me 2.56 meter per second. That's the common velocity of the two. Okay? Okay, good. Now, the second part is a little bit harder. He says, suppose the collision between the packages is perfectly elastic. Aha. So what's going to happen before I even finish the statement? What's going to happen? Let's go back to the diagram. So what's going to happen here is that this package, the package M, is going to hit this one. This is going to go straight line this way, and this is going to rebound this way. Make sense? Because it's lighter. So that's going to go this way, and that's going to go this way. Now, okay, suppose the collision between the two packages is perfectly elastic. To what height does the package of mass M rebound? So it's going to go up to what height? Okay, that's very interesting. Well, all I need is to find what is the velocity of it going back, and then I use conservation of energy. I hope you see that already. Okay, so how do we do that? Well, let's see. Again, I'm going to draw a picture of how it looks like. The first picture is basically this picture. This one, which is similar to the inelastic. And we're going to have the same numbers. So BC is going to look something like that. Here is M moving with velocity v, the one we just calculated, and here is the mass 2m here. This is m, and initial velocity is 0. Okay, this is all BC before collision. Now AC, we have a different picture. The AC is going to be the 2m is going to move with one velocity this way, v prime, okay? And then the m is going to move rebound this way. We're going to call, let me call it v2 prime, and this one v prime, going this way. I hope this is not confusing for you. Okay? Maybe 1. Call that 1 and 2. I don't know. There we go. Okay? Of course, this is m, this is 2m. So that's AC. Okay? So in this case, when I apply momentum, that's going to be mv, which is this one is 0, equals to minus mv1 prime plus 2mv2 prime. There we go. Masses cancel out. I end up with v equals minus v1 prime plus 2v2 prime. I have this equation. As you can see here, it is a difficult equation to solve because I have two unknowns. Elastic is always hard. Okay? So how do we do this problem? So what do we do in this case then? Well, we can go back and appeal to the equations that I have showed you. But let me just move on with it. Let's assume that I don't have those equations. What else I can get? Well, since it's elastic, remember we said that the sum of the kinetic energy before and after is the same, are equal, right? So I can say that. Let's go to BC right here. So what are they explicitly? That's going to be 1/2 mv squared plus 0. There's no kinetic energy in the second package because it's 0. Equals to here and here. That's going to be 1/2 mv1 prime squared plus 1/2 2m v prime 2 squared. Okay, the m's cancel out, the half cancel out. I end up with v squared equals to v1 prime squared plus 2v2 prime squared. Okay, as you can see, I have here now this ugly equation, difficult equation to solve. I have those two. Both of them are simultaneous equation. I mean, I know v, which is this number right there, the v right here, 7.67, right? So I can put it in there, no problem. Then I have two unknowns, two equations. I can solve it, but guess what? It's going to take you a whole page of calculation to get V1 and V1 prime and V2 prime. Okay? So what I'm going to do, I'm going to appeal to the equation that I have showed you under hyperphysics. Go back to it. Here it is. This one right here. Okay? Remember, the 2m, which is m2, is a target. I can do this one, if you will. He said here, collision target initially at thread. That's what we have, really. So basically, there it is right there. Okay? So this is the initial velocity, excuse me, the final velocity of m after collision. He's not asking me for this one. So all I need is just to plug in this number, this equation right here. The difference between the two masses divided by V1, which is V for us. So let me put this on the side. What is it? Right there. This one right here, guys. So that's the one I'm going to use. So again, I can either, I mean, you are free to use those two and solve simultaneously. Or the cheap way is basically use those formulas, okay? So here we have V1 prime. This is the notation that I'm using right here, guys. V1 prime. And this V1 is basically the V here, is equal to the difference between the two masses, M1 minus M2, over the sum, M1 plus M2 times V, right here. And I got everything in there. So all I need is to plug in my, so I have here M minus 2M over M plus 2M times V, which is 7.67, right? Right here. Right there. See it? And that's it. The M's cancel out. I end up with minus M over 3M. M's cancel out. 7.67. Sorry, I'm writing too fast. Like that. And then you'll end up with negative 2.56 meters per second. There we go. In other words, what I am trying to tell you is that when the block, where's the picture right here? When block 1 rebound is going to shoot with V1 prime equals to negative 2.56 right there. But that's not what he's asking me. He said to what height it will go. To what height. Okay? In other words, if I would continue this picture, let me put a different color to it. If I continue this picture right here, it's going to go like that, right? So to what height is going to come here? This height. H prime, let's call it H prime. Okay, so again, we're going to use what? Conservation of energy. Here, at the level ground, I have kinetic energy. Here, it's going to what height? This is going to stop. It's all potential energy. So that's what I'm going to be using. So going back, so use conservation of energy. 1/2 mv prime squared prime, v1 prime, equals to mgh prime. I hope you understand that. And then we just cancel the m's here. So the height h prime is going to be equal to what is it? V1 prime squared over 2g. And then we just plug it in. So we have here 2.56 squared divided by 2 times 9.8. And then we calculate that. And it's about 0.33 meters. Or roughly is 33 centimeter. And there we go. Okay? Okay, good. I think I'm going to stop here, and I'll see you in the next video. Bye-bye.